Hi all, myself Anoop, and along with me there is Ram. We both work with Intel Big Data team and based on Bangalore, India. So in the, I think 2 talks before this, we could hear about this particular work of off-heaping the read path. So I'll just explain about something more in detail about what kind of steps we have taken and what is it all about. And we will be having some sort of performance numbers, what gain we are getting because of this. So coming to the overview part, we all know that there is an L1 cache and an L2 cache in HBase. L1 cache is nothing but a LRU on-heap memory structure where we will be keeping the H file blocks and evicted like as per the need. And L2 also we call it as bucket cache, which is having different modes, like the actual data can be in on-heap, in off-heap, it can be in a file. So basically, as we are speaking about the off-heaping work, I will touch only the off-heap area. So there is L2 off-heap cache. So the advantage is it can be much bigger because we are not very much constrained with Java's maximum heap size, or when the heap size is more, the impact of GC, it's not that predictable. So we can get rid of most of such things. That is the advantage what we have with L2 off-heap bucket cache. So the figure just shows how the bucket cache is being arranged. So in bucket cache, we can see there is a logical split of the entire memory area into different buckets, as well as the entire, say, the GBs of memory is split into, say, 4 MB chunks, nothing but the byte buffers. And logically, it is being split into different sized buckets. A bucket is nothing but, we know that H file is being split into H file blocks of by default 64 KB size. So in order to accommodate these kind of different sized H file block buckets, we will be splitting H file blocks, we will be splitting it into logically, say, starting from, this is default, all default values, like 5 KB sized buckets, we have 9 KB sized buckets. Like that, we have till 513 KB sized. So every bucket can again, every bucket is having again slices, like each slice means a slice can actually accommodate one H file block. So the calculation there is at least every bucket should have 4 slots. That means when the maximum size is like 513 KB, it's 513 KB into 4, that means 2000 something, that much size KB, and that is being split into 513 KB sized 4 slots. Like that, the same size, 2000 whatever it be, is given for the 5 KB buckets also, like 64 KB buckets also. So like that, we'll be having more slots there. So from the figure itself, we can see that and whenever there is a need for caching a block, the algorithm will try to find the best fit, like where I can best fit, which bucket I can best fit based on the H file block size which is incoming for the caching purpose. And it will be placed to a slot within that particular bucket. Okay. And as per this sizing, we can see that there is always a chance that when we write a particular H file block into a slot, it can span. It need not be within one byte buffer. It can span across 2 byte buffers also. So, so that is about the overview. So in the last talk also, Deepankar was just mentioning, like when we are using the bucket cache in the off-heap mode, say whenever we are hitting one H file block which is there in this off-heap bucket cache, we had to copy it, the entire block. So say if the default numbers, if I take it is 64 KB. So the entire 64 KB of the off heap, that much bytes need to be copied to a temporary byte array, which is obviously in the on heap area, and a block has to be constructed, and then I have to get the cells out of that, and I have to return it back. Say for when we are doing say random gets of rows, like say some 3 or 4 cells in a row, there is no other go. We have to copy the entire 64 KB because at that layer there is nothing like cell. It's only H file blocks. We have to copy the entire thing, and then we have to create cells, and whatever the cells belonging to that particular row key, we have to return it via the RPC. So there were a lot of this kind of copy and intermediate, the temporary byte arrays of creations, which is creating a lot of garbage into the system. So, and one more thing, and not just this, there is another issue also why we have to copy is that the read path, the entire read path was having an assumption that the H files data is backed in on heap in a byte array, because at many places we try to deal with byte arrays. So if you have no other go, when the data H file block data which is being cached, which is in the off heap area, there is no other go. You have to copy it. And another thing is, as we know, we have cells. We got rid of key value from 0.96 onwards. We are having cells, but still the cell is expecting each of its fragments, like say row key or family. It has to be in the on heap byte array, because all the getters we have, say get row array, say we have get value array, like that, all are returning byte arrays. The return type is byte array. So there is a assumption of that way. So these are the because of these mainly two three points, we had to copy the off heap block, the block which is there in the off heap cache to the on heap whenever the read path, the reader is hitting that particular thing. So just trying to picturize the things in this. So we have the bucket cache here, which is off heap. So we say we can have say one H file block which is there in 1 byte buffer itself. It can be spanning across 2 byte buffers also. Whatever be the case, we had to copy it temporarily to a byte array, create an H file block, and pass it to the scanner layers, which will do all the work of finding out the cells which need to be returned, and things were happening like that. And in our main agenda, our main goal was to do it this way. Whenever we are using an off-heap bucket cache, do not do any copy. Just return it from there itself. The cell bytes are actually there in off-heap area. It will not be copied to the on-heap area until and unless it comes to the RPC layer. So within the RPC layer also, it will try to return from the off-heap area only. So we can save a lot of like this temporary copy avoiding, and so garbage. Okay. So in this, now I'll try to explain like the steps we have done for the building up of this entire solution. So the first thing what we tried is selection of a data structure around the off-heap area, which we can use to pass through this entire layer. So before we are starting this work, we were starting this work itself. It's like bucket cache is there. As I said, it's been split into byte buffers. So we are using Java NAO byte buffer only. So, but the thing is, at that point of time, whenever there is a hit, it will be copied to the on-heap area. So then onwards, the scanner layer always deals with on-heap byte arrays only. But right now, as per our change, what we have seen here, So it will be always happening. It will be dealing always with the off-heap memory area. So as we know that in HBase read, there are a lot of compare operations. We have to order the cells properly. So there will be a lot of Rocky compare. There will be family compare. A lot of compare operations are there. So the selection of a data structure is very important. Like how fast is the read from that particular data structure. So in this aspect, we have done some sort of benchmarking test with this NIOS, Java NIOS byte buffer against NetEase byte buff, because there is always this thing that Java NIO byte buffer is having a lot of overheads. That's what people used to complain a lot. But here it is, byte buffer is not the heap byte buffer, it's the direct byte buffer because it is off heap. So we have done test of this thing, NIO direct byte buffer versus NetEase direct, its equivalent part. So this is what the JMH benchmark has given us. So it's very clear that we are seeing that, no, it's not true that NIO's or NIO byte buffer is bad. It's somewhat better, that's what we have seen. Again, it's on the direct byte buffer, not on the heap byte buffer. When we compare on the heap byte buffer, things are different. NetEase heap byte buffer is much, much better than NIOS. And also, we can see in HBase, the read paths, we will try to do as much as possible the unsafe kind of operations, which is giving much better throughput for us. So we have done some sort of testing there. So both are like unsafe. It's pretty close, like it's almost same, we can say. So the conclusion here was that it's fine. We can continue with the NIOS DBB. It's fine. No need of any change of a data structure. This was the first step we have done. The next step was to make the stage ready for the off-heap end-to-end path. So when we started the work, as I said, it was already cells were in place. See, prior to 96 version, we had key value, which was expecting the entire row key followed by column family, the value, everything to be backed by a single byte array data structure. So we got rid of that by 96 itself. We introduced the cells. So cells no longer demand that kind of an assumption. It can be like your row key can be in one place, your value can be served from another place, another byte array. So, but still it was not fully done, the cellification. The first step we have done is using these JIRAs, we made sure that in the entire read path, cells are flowing. So there is no need of no key value assumption at any point of time. The next thing was H-file blocks. In certain places, as I said, the read path was having an assumptions that the H-file blocks data structure is actually a byte array. So that we got rid of and we replaced it with it can be byte buffer, so that I can have an on-heap byte buffer as well as I can have an off-heap byte buffer. The next thing, we already saw that in cell at least there is an assumption that everything is byte array based. So we extended the cell. So it's not like we added new APIs to the cell. Because cell is public exposed, it is used in the client end also. We did not want to add any off-heaping stuff, at least as of now in the client end. Everything is happening in the server end. So we extended the cell to have a byte buffered cell, a new abstraction, and in which we added equivalence of this get row array, get XX, that array to a get byte buffer also, which can return directly a byte buffer. So this is there only in the server. In the client end, you will never see that kind of a, cell type. Okay. And we added cell in utility APIs such that it can deal with, it will basically type check what is this incoming cell. So if it is a byte buffer backed cell, it will try to use the getters which returns byte buffer rather than byte array, because byte array based APIs are still working on that new type of cell implementation, but still it need a temporary on heap copy, so which can create a lot of garbage. So the cell util will try to avoid that particular thing. So this as just a note I just added. In case of these are like public exposed filters and our region observer coprocessor. So there were two places we were having this byte array. So say in post scanner filter row, in filter row key itself, like we were passing the byte array. So anyway, when a filter is there in place, we have to call that API again. We will end up in copying the data. So we just got rid of by deprecating that and adding a new API which is passing against cells. So our advice when people are moving to 2.0 is that please do not use the deprecated API. Please move to the new APIs. So with this, there are for a few more building block steps what we have done, and then the performance evaluation, some of the test results, whatever we are having. So I am just handing over to Ram to take it further.
So hi everyone, we'll continue with this building blocks. So as Anoop said, so the entire code base has been changed and moved over to the cell based concepts. So there is no more key values. So but if you see, because we had key values, all the comparisons were done by the key value comparator, again based on the assumption that the things are based on byte arrays. So we had to change that, and we introduced the concept of cell comparator, which will actually abstract out the logic whether the underlying cell is backed by a byte array or by a byte buffer. So that was the next step that we did. So after once we did that, so as you know, like there are a lot of comparisons that happens in retrieving a given cell. So you need to search and you need to compare the rows, the previous row, the next row, then the families to know whether we have moved over to the next cell, the next row. So comparison was a key operation. So for that, we have to now decide, like all this while it was all byte arrays and we were doing some unsafe based comparisons on those key values. Now if suppose we are moving to cell and assume that cell is backed by an off-heap byte buffer, so how does the comparison work out? Is it like giving us a poor performance, or it is equivalent to what the byte arrays were giving? So we again did a JMH based micro benchmark, and we were able to see that an off-heap compare and on-heap compare were like almost similar. So there was no performance overhead comparing the off-heap backed cells and the byte array, because all are unsafe based operations here. So the building block is like key values were converted to cells, and all the cells need a comparator, and so we moved over to cell comparator. And then all these initial steps helped in building the base, and the foundation was laid, and from there we have to just assume that the entire read path is now cell and see how the bucket cache fits into that. So as we saw in the first diagram, so any bucket cache will have some byte buffers, and a block can span across 2 byte buffers. So now our priority, our main aim is not to do this copy at any point of time. So the data structure that we need to now replace this byte array, which was initially representing the H file block, has to be changed to byte buffers. So that byte buffers can be again the direct byte buffer or an on-heap byte buffer. So we introduced a concept, a wrapper over the NIO byte buffer, because NIO byte buffers cannot be extended. If Java had provided us that option, then we need not have created the wrapper called byte buff. So the name is BYTE-BUFF. This is just to avoid conflict with the NetEase byte buffer. So this wrapper class is nothing but it creates 2 types of byte buffer. One is called a single byte buff, and other one is multi-byte buff. So where do you get this single byte buff? So in the case where you are reading from HDFS, so there is nothing in your bucket cache, things are being read from the HDFS, so it is going to form an H file block. In that case, you can definitely wrap your entire H file block with a normal on-heap byte buffer. So that comes under the single byte buff. And when your reads are getting served from the bucket cache, so there is a possibility that your data can span across 2 byte buffers. So there we have the concept of multi-byte buff. So this is nothing but a wrapper on the NIO byte buffer, and it has two things. One is the normal on-heap byte buffer, the other one is where you have multiple byte buffers combined together to form an H file block. So the next aim was to change the H file block data structure to work with this byte buff type. So that was the next step. So all the building blocks were done. So now the next problem is we had an eviction logic in the bucket cache where any block that follows the LRU pattern gets evicted. So now in our case, since in the previous code things were getting copied on heap, so you immediately you know that the H file block that you are working with is on heap and the bucket cache area can be actually freed. So the bucket cache byte buffers and offset, the offset from which a block is written can be overwritten with a new one because it can be considered as evicted based on the LRU logic. But now that assumption is not valid because you still have references to a particular block. If the scan is a bigger scan, you still keep referring to that particular block till you are sending out the result in the RPC layer. So we cannot assume that since a block is least recently used and it can be evicted as soon as possible. So what we do is every time a block is referred, we associate a reference counting mechanism with it and we keep incrementing it. And as you see, when a particular block is being read and the data is read out and the results are formed and we write the results to the RPC layer, we again do a callback sort of mechanism from the RPC layer to the underlying scanner layers which was involved in that particular scan. So that callback traverses back till your H file layer, block cache layer. So there we do the decrementing part. So this is a simple reference counting mechanism that we try to do and ensure that the eviction does not happen till the reference count becomes 0. So this ensures that any block that we are referring is not evicted and we are able to serve the read and only then those blocks get ready for eviction. So after all these things were done, this is the complete picture that you get. So the callback that happens from the RPC layer flows through the scanner and then you have the reference counting that is getting decremented. So first time when you access, the reference is incremented, on the callback flow it gets decremented. So unless and otherwise the ref count is not 0, that block is not considered to be evicted. So we'll move on to the results. So to start with, we did some experiments with the performance evaluation tool and also we did some experiments with the YCSB. Here it's just a single region server setup and the RAM 150, you can see the cluster setup also. So we had a off-heap size as 105 GB, heap size is only 9 GB. What we ensured is whatever we loaded, so it's a pure workload testing, read workload testing. So once we wrote all the data, we ensured that all the data is loaded into the cache, in this case the bucket cache, and we were able to check the multi-get operation here. So you can see the improvement that you get. So this is the average completion time. So the lower the better. So this is with respect to scans. So in scan you can see that we have been using this filter all option. This is mainly because we want to avoid the impact that we get on the results due to the network bottleneck when the results are sent out to the client. So we just use the filter all option in the filter to see how the server alone performs after all these changes. So again, here again you can see a good performance with respect to this off-heap read path. And this third result is again scans, but if you see we are adding a customized filter which will actually return back only 10% of the results to the client. This is in case of like Phoenix where you really have some set of data alone to be filtered out, and to test that scenario we did this, and here again the data is loaded into bucket cache and it is pure read tests. And this is with YCSB. So the similar setup, and we tested for YCSB get and for YCSB, and with this is workload C, that is pure reads, and we also tested for scans. So you can see the improvement, and we customized YCSB to support multi-gets, and you could see the performance here. So the readings have been also captured for different threads. So the important thing is, once you see that the number of threads keeps increasing, you are actually able to get much more better performance, whereas in the previous case, like, they were not able to perform because of the lot of garbage that was getting generated because of the copy that was happening. So this test is basically to say, like, we want to ensure that this feature gets enabled in the 2.0 release. So the best comparison to do is, how does this fare with L1, the current LRU cache. So this was a test like done with just less data, but with the minimum data, but the idea was to check how does the bucket cache and LRU cache work, and which one fares better. So with this, you can clearly see that once the number of threads are increased, we still see this L2 is performing much better, and added to that, you are able to reduce your heap size. So whatever you are doing with 32 GB, you are able to do with 12 GB, and you get more performance. Like, see, the operations are also like 10 million operations, which is done in the this is multi-get, right? Yeah, this is multi-get. So you can see the GC graphs. I think I'm not sure whether it's pretty clear here. So you can see the GC reductions here, young GC reductions. It was like for a multi-get, so like 102, it has come down to 8. So this basically, this whole work is to avoid this minor GCs, and this is what the other talk that happened by Rocket Fuel was. They were trying to target this particular area. Similar with scans, you can see the reduction in the GCs. So what about this feature, when it will be available, is we are targeting that this should be available in 2.0, and the other thing is, as we showed in the previous slides, this is similar in performance to LRU, and sometimes even better. We try to make this as a default, this in 2.0, and as I said, Rocket Fuel has already done a backporting of this version particularly for the random read workload. And we have more details and other benchmarking results and the micro benchmarks that we did in this particular blog, Apache blog. So what is the future work is, we are focusing on the right path of heaping. We are in progress doing stuff with that, and off-heap MS lab pool, and creating currently the request is like, we every time we dynamically allocate a byte buffer and the requests are served through that, but we want to avoid that and see if we can serve requests from a pool, and again try to make that also off heap. And there are some protobuf changes. There are some challenges here, because currently protobufs works only with on heap. So though you are changing the other layer, like RPC layer, to work with off heap, but the protobuf will anyway try to copy it on heap. So we are trying to work in this area. And the last one is the in-memory flushes and compactions. This is going to be a very good add-on, because at least even their use case is like there are a lot of duplicates. Even if you don't have lot of duplicates, the indexing mechanism that they are adopting will be of greater use in doing this off-heap work. Because what we observed is, though the cells are moved off-heap, the concurrent skip list map is definitely having a overhead. So when you have lot of small sized cells, those cells are like, and 128 MB is your flush size, almost 50% gets accounted due to the overhead of the concurrent skip list map and the cells references and the pointers to the cells. So if the this design done by Yahoo team for the compaction, in-memory compaction, and the indexing mechanism of the cells into the pipelines will be definitely helpful in this off-heap work, so that we can do a proper accounting of the memory. So this is how this all it's about. So any questions and doubts?